Let's do a couple of examples working with probability density functions and cumulative distribution functions. The first example is a very simple one. We have a 100 kilogram point load that is equally likely to be placed on any point along a 10-meter beam. So here's our 10-meter beam, and here's that point load right here. So anywhere from 0 to 10. So x is our random variable. That's going to be the location of the point load along the beam. And so let's just go ahead and define this. So for x being between 0 and 10, let's define our PDF, our probability density function. So little f, big X, little x is equal to some value. We don't actually know what it is yet. We're actually going to solve for that. Some value for x being between 0 and 10, and then 0 otherwise. So if we're outside of that, we're not on the beam, and it doesn't matter. And we can draw this real quickly. Okay, so here's x, here's some value c, this is our PDF, and then our value, this is just uniform, it's called a uniform distribution, all the way to 10. So equally likely just means it's flat. The probability density is flat. So now the question is, find C. What is that value of our uniform for the uniform PDF? We'll go back to the definition of the PDF. So the definition is that for a PDF, our function, if we integrate it from 0 to the basically upper bounds, in this case of x, we could say positive infinity, or we could just say whatever the upper bound of x is. In this case, it's 10 of little f of x, or distribution function, or density function, dx, that should equal 1. So the area under this curve should equal 1. Kind of a mathematical definition of that. So we can actually do that, and we'll just say, okay, our from 0 to 10, our function is just a constant, c, dx is equal to 1. And so that is, if we integrate it, we should just get cx from 0 to 10 is equal to 1. And then this just ends up being 10c is equal to 1, and then c is equal to 0.1. So now we can go back in there and erase that variable and put in the value of 0.1. So that is our uniform distribution. The next thing we can do is find the CDF. The cumulative distribution function for that. We denote that as big F of x. And we can say that this is the integral of our f of x from 0 to x. All it is saying is that if we want to evaluate the cumulative distribution function at a particular value of x, then we integrate the PDF up to x, and we keep that as a variable, because that then will give us a function. So we know, and we've already integrated this, we know that this is equal to cx when you integrate it. And we know that c is equal to 1/10. So big F of x is equal to x over 10, or 0.1x. And so it's just a line with that slope. And that makes sense, right? If we integrate a constant, then we get a line. So let's do that. And we have x over here. We're just going to draw it out on a graph. We start at 0, we go to 10, and then we know that we're going to reach 10. The cumulative distribution function will be 1. So our slope is equal to 0.1. And then once we reach that, we bottom out, and it's just 1 after that, because we can't go above 1 in terms of probability. We can use this cumulative distribution function to show or calculate the probability that x falls between some values. So what's the probability that our point load falls between 2 and 5 meters? That's going to be just the integral from 2 to 5 of 1/10 dx. And that's going to equal 5/10 minus 2/10, or 3/10, 0.3. So we can do that. Note that this is also equal to the cumulative distribution function evaluated at those two values, right? And what that is basically, so if we just wrote it over here, we could say this is 2, 5, and we're getting here, this is big F at 2, and then this is big F at 5. And if we were to do this integral, we're calculating the area on the curve, the PDF, up to 5, and then we're subtracting out that area up to 2. Let's do one more example. In this second example, we'll consider the useful life in hours of a welding machine, or any machine. It's described by the exponential distribution. We'll define that in a second. So the exponential distribution is a certain kind of PDF. We'll let our random variable big T equal the time in hours that the welding machine works. And then I'll give you the exponential distribution here. So the PDF of the exponential distribution is lambda, which is a constant, times e to the negative lambda t. So little t is a particular time that we have, that we are considering, and this can tell us the probability of the machine working up to that point. So lambda, in this case, we're going to give you is lambda is 0.07, so that's a constant. Let's draw this distribution out. So here is our random variable t, and we'll just say that it can range from 0 to 100 to 200, 300 hours. And then here is our density values. And then the distribution, that is just exponential decay, so it looks like something like this. I don't know how quickly it decays, but it's going to go over there to some point. And then we can also draw out the cumulative distribution function. So this is our PDF, our probability density function. Here's our CDF, cumulative distribution function. Big F of t And that's going to go from 0 to 1. And it's going to look something like this. So if this is 1, we'll just trace that across. Then it's going to come up here and asymptotically hit 1 and not go above 1. So we're given the PDF. We can find the CDF by integrating to a variable t. And the CDF becomes, if you do this integral out, you get 1 minus e to the negative lambda t. So we're just subtracting whatever this is from 1, and eventually this gets so small that we essentially get 1, right, as t becomes really big. So as t approaches infinity, f of t, the cumulative distribution function, approaches 1. So now let's find a particular probability that we might be interested in. Let's find the probability that t is greater than or equal to 100 hours. So normally when we think about the cumulative distribution function, that is ft of t is equal to the probability that t is less than or equal to some value, right? I don't need to write that in, I'll just keep it as t. So we can rewrite this to fit that. So I'll kind of put it down here. So the probability that t is greater than or equal to 100 is equal to just the complement of the CDF, 1 minus probability that t is less than or equal to 100. And then this is just 1 minus the cumulative distribution function evaluated at 100. So we define that above already. Here's our cumulative distribution function for the exponential distribution. So we can say this is 1 minus e to the negative lambda t. And then we'll plug our numbers in. 1 minus e to the negative 0.07 times 100. And then this ends up being 0.00091. So that's our probability right there. And let's just look at what we did on the cumulative distribution function. So we're interested in what the value is above this particular value. So we can evaluate, this is ft at 100 right here, whatever that value is. But we're interested in basically everything above that. So we're interested in, this is 1 minus 100.